Okay, so in this video, we're going to take a look through the OCR specification, starting with gravitational fields, but then moving on to astrophysics and cosmology. So some guidance in terms of using this video. So this is designed for people who have finished working their way through the A-level course, for you to review and improve your knowledge. And you should be using the template I provided, and there's a link to it in the description, to grab a copy of the template you can see on the right hand side and work your way through it before you review it using this video. And lastly, that process of going through, finding out how much you can produce and finding out where there are gaps is something that you should do regularly as part of your revision. So to help with that as well, I've created some resources to go along with that. So I've created one resource looking at fields and another looking at astrophysics and cosmology. Links to both are in the description to this video to help you get to the point where you can recall them with no effort. All right. So let's start off with gravitational fields and how we can model them. So these are the points the specification says you should know or be able to do. So let's start off with describing what a gravitational field is. But as I said, what I'd like to do is just pause the video now, work your way through the template in the description, and then we'll review the sections so you can see where you need to improve. So gravitational field. So the area around an object with mass where another mass would experience a gravitational force. So every mass has one of these, and every field for a gravitational force anyway is actually infinite. So every mass experiences a force from every other mass in the universe. So when we're modeling gravitational fields, one of the important things to know is where the center of mass of an object is, and therefore what a center of mass is. So center of mass is the point where you can model the mass of an object to be concentrated. So if something is uniform density, that's really easy. It's at the geometric center. But for some other objects, it's more complicated than that. And that's something you learn more about in M2 in mechanics and maths. So there are two types of gravitational field you come across. A radial field, where you can see the field lines spreading out from a point. And then you have uniform gravitational fields where the field lines are parallel and equally spread. So the thing they have in common is the field lines always go from high potential energy or from zero potential energy to low where it's negative close to the object there. So the field lines are always go from essentially far away or infinite to where the lowest point. So one of the ways we use to describe a gravitational field or a point in the gravitational field is the gravitational field strength. And that is the force experienced by a unit point mass in a gravitational field. So unit means 1 kilogram, point means it has 0 volume, or we're modeling it as having 0 volume. So in terms of practically thinking about how two objects exert gravitational forces on each other, so gravitational fields are infinite range. So the gravitational field of all masses are interacting. And when you have two of the same fields interacting, they create a force between the two objects creating them. And then in terms of the actual mechanics of how it works, the way we model it at the moment is we say the two masses that exchange graviton, which is the exchange particle of gravity. It travels at the speed of light between them, and that's what allows them to exert a force without being in contact, and it is mediated incredibly quickly. So for objects close to us, we think of it as being instantaneous. All right, so looking at some ways we actually model gravitation using Newton's laws. So first of all, Newton's law of gravitation, it tells us the two factors that affect the force of gravity, the product of their masses and the product of their distance between their centers of mass. And it's directly proportional to the product of the masses and inversely proportional to the distance squared. So we can calculate the field strength using an equation for a radial field. It looks something like this. So field strength is defined in terms of unit mass. So we make the little m equal to 1 essentially, and that gives us field strength that we usually use a little g as a symbol for. So on Earth, we model gravity as being a uniform field on Earth, so the field strength is the same everywhere. So the force per unit mass is going to be the weight force of the object divided by the mass, which you can see is just going to be equal to G, the value G, 9.81, but it's force per mass, so newtons per kilogram. Okay, so now moving on to modelling planets and the laws that govern that. So first of all, starting off with Kepler's laws that we use to describe the motion. So his first law says that all the planets in the solar system move in elliptical orbits, and you should know that an ellipse has two foci, and that Kepler's first law says the Sun is located at one of them. So the second law states that the line connecting a planet to the Sun sweeps a constant area per unit time. So you kind of have to draw a picture, so you can draw a radius, and then a period of time later, the radius will be in a different direction, and the area it's talking about is the area between the two radii. And then the third law, which is probably the most commonly one used, says that the square of any orbit time period is directly proportional to the cube of the semi-major axis, which means the largest radius of its orbit, which is a useful relationship. So first of all, we need to think about why planets are actually in orbit around the Sun, and we can use some of our knowledge from circular motion to get an idea for this. So the Sun exerts a gravitational force on the objects in the solar system, and this force is always perpendicular to their velocity, so it's a centripetal force. And what that does is it causes the planets not to move in a circle because their speed and their radius changes, but it makes them move in an elliptical orbit around the Sun. And in terms of planets, they have to obey Kepler's third law. So for the planets, we can find, if we know the time period, we can find out how far they are from the Sun. Okay, so what I'm going to do now is get you to come up with a question to exemplify the use of Kepler's third law. So what I'd like you to do is pause the video and have a think of a scenario you could get someone to do a question to show that they understand Kepler's third law, and then I'll show you an example that I came up with to demonstrate it. Okay, so my example was calculating the time period of a satellite with double the time period of a geostationary satellite. So the first thing we're going to do is say, okay, well, a geostationary satellite has a time period of 1 day. So that must mean the satellite has a time period of 2 days. And so if we apply Kepler's third law, we get the expression that you can see there, which we can rearrange to make an expression for the radius of the satellite. Okay, so now what we're going to do is have to figure out the radius of a geostationary satellite, which we can do using some circular motion. And we're going to replace angular velocity with 2 pi over t. And we're going to rearrange it all to make the radius of a geostationary satellite the subject, so we can get its value. And once we know the value, we can plug that in and work out the radius of the actual satellite with double the time period then. Okay, so moving on, so let's explain what I meant by a geostationary satellite. So it's a satellite with the same time period as the Earth's rotation about its own axis, or essentially what that means is the same angular velocity as the Earth. And these have quite a few functions, which is why there are a lot of them in orbit around the Earth, but most of them are in some form of communication. So we use them for mobile phones, for television, for the internet, anything we want to be able to point an aerial at a fixed point in the sky, and it always to be pointing at the same satellite. And as I showed you in the example, we can work out how far away we need to put geostationary satellites, and we can also work out how fast we need to make them travel as well. But that's how we can figure out how far away they are. All right, so now we're going to think about gravitational fields in terms of energy as well as in terms of force, which we've done already. All right, so starting off with gravitational potential, in terms of what that means, it's the work you have to do to move a unit, so 1 kilogram point, so 0 volume mass, from infinity, where it has no GPE, to a point in a gravitational field where it does have some GPE. And we can calculate it using an equation. So the symbol used for potential is V, just like we do in circuitry, we use V for potential difference. And we can calculate it if we know the mass that's creating the field and we know how far we are from its center of mass. So in terms of the relationship that we have there and linking it to field strength that we've seen before. So field strength is the gradient of a potential versus distance graph, or another way of saying that is it's the derivative of potential with respect to distance. In terms of doing it the other way around, we can calculate the change in potential if we find the area under a field strength versus distance graph. Or another way of saying that is the change in potential is the integral of a field strength with respect to distance. So if we know potential, we can very easily calculate potential energy by multiplying it by the mass that's in the field, and you end up with the equation you can see there. And we can use potential energy as a way of working out how fast something needs to travel to escape from a given gravitational field. And we do that by equating kinetic energy to GP. So we need to give it enough kinetic energy that it can do enough work to escape, and then rearrange it to make V the subject, and that gives us the escape velocity. And different objects have different size. The bigger your escape velocity is, the stronger the field is, as a general rule. Okay, so now we're going to move on to look at some astrophysics and starting off with stars. So first, let's define some terminology. So again, as with all the other sections, I like you to pause it and work your way through the video, and then we'll review each section. All right, so now you've got your definitions, or at least your attempt at them. A planet is a body that's in orbit around a star, but has cleared its own orbit of other orbiting bodies. That's what our definition is, and this is why Pluto stopped becoming a planet, because it doesn't fit that definition in. A planetary satellite is something that is in orbit around a planet. And then comets are slightly different. So they are usually an elongated path or elliptical orbits, and they are made mostly of ice and dust. And we can see them mostly by the tail of gas they produce when they get near the sun, when the ice starts to evaporate. The solar system is used to refer to the planets around the sun. So the 8 planets, they're moons, and along with all the asteroids, meteoroids, and comets that are also in orbit around the sun. Scaling up quite a bit in terms of a galaxy is a collection of stars, and also with the gas and dust that are also inside and around them, and they're all held together by their gravitational attraction. And also we use the concept of dark matter to explain how they are held together as well, because the gravity of matter is not enough. And then finally, on the largest possible scale, the scale of the universe, and that's all existing matter and the space in which it is contained. So the universe is everything that exists, essentially. So what we're going to look at is, first of all, how the first stars formed and how stars still form today. So we start with stars with a nebula or a cloud of gas. And what happens is the gas has mass, so it's pulled together by gravity, and its density starts to increase, and that's called gravitational collapse. So as they get pulled together, that means the gas is losing GP, and applying conservation of energy, we know that has to be transferred into something, and it happens to be transferred into kinetic energy. And you should know from thermal physics that with a gas, if you increase the kinetic energy, that means the temperature of the gas would be increasing, so it's getting hotter. So eventually, the gas will have high enough kinetic energy that nuclear fusion starts to undergo, because it has enough kinetic energy to overcome the repulsion between the nuclei. And this fusion process produces photons, which are absorbed by the outer layers of gas. And that absorption process exerts what we call radiation pressure. And that's what keeps the star in an equilibrium state for billions of years. And that's what the sun is currently at. So Next, we're going to have a look at some of the different processes by which stars end their life. So our sun is going to eventually become a white dwarf. So first thing that's going to happen is it's going to run out of hydrogen, or get very close to running out of hydrogen. And what that means is the radiation pressure drops, so it starts to collapse. And it will keep collapsing until the temperature is high enough for helium to start undergoing fusion. So that's the next process. And the fusion of helium releases a massive amount of energy, and you have a massive radiation pressure that forces the star to rapidly expand. And it starts to cool down as well as it expands. And that's why the radiation wavelength will increase as it cools down. We're using Wien's law there. And that's why it looks red, and you formed a red giant. And then finally what happens is the center, or the core of the star, when you form a red giant, is going to collapse, and it will keep collapsing until there's enough outward force from electrons trying to be forced into the same quantum state for it to again reach a balance, and then it will just stay like that till pretty much the end of time. So in terms of like what a white dwarf looks like, so it'll have a very similar mass to the original star, but because it's in a much smaller volume, it's going to have a much higher density. In terms of its luminosity, it will be very dim because there's no fusion happening on it anymore, and its temperature is going to decrease over time. So although it's initially quite hot, its temperature will decrease over time, and it will basically become inactive and not do very much, so it becomes quite boring. So the more exciting space events, which happen to the bigger stars, so both a neutron star and a black hole undergo a process called a supernova. And that happens when the mass of a star is big enough that as it collapses, when it runs out of hydrogen, it can collapse far enough and the temperature rise far enough that the heavier elements start to fuse. And we describe the mass at which something needs to start undergoing this process as the Chandrasekhar limit. So that tells you whether it's going to become a white dwarf or form a supernova. And if you are in the situation that produces the energy from the fusion of heavier elements, creates a massive shock wave, and it sends a large amount of matter into surrounding space. So both a neutron star and a black hole form from what is left behind after a supernova. So a neutron star is the core of the red supergiant that is formed, and because the mass is large enough, you can actually overcome the electron degeneracy pressure. And so what happens is you get protons decaying to become neutrons, and that's why it's described as a neutron star, because it's made of just neutrons. And because the whole star is made of neutrons, it's incredibly dense, and it has the same density as a nucleus does. A black hole happens to even bigger mass stars. So the reason a neutron star stops collapsing is because you get neutron degeneracy pressure, so stopping neutrons occupying the same quantum state. But the mass is so big you can even overcome that, and it collapses the mass into a single point called a singularity. And it creates a region around the singularity where the escape velocity, or the speed you need to escape from the field, is greater than the speed of light, which means nothing can escape because nothing is able to travel through space faster than the speed of light. Okay, so we can illustrate all of these different processes on something called a Hertzsprung-Russell diagram. So in the middle and the diagonal line, we have what we call main sequence stars, which are stars in their equilibrium state. So our sun is on this sequence, but we can have a whole range of different sizes and luminosities. So something I'd draw your attention to is on the bottom, it goes from low temperature to high temperature as you go across to the left, whereas as you go upwards, you increase the luminosity. So what you can see is that the red giants and the red supergiants are cooler than the main sequence and white dwarfs, which is what we said earlier, but they are also much more luminous, which means they are brighter. Whereas white dwarfs, we can see at least initially, they are much hotter, but they are much dimmer because, as we described them, their luminosity is quite low, but over time their temperature would decrease. So this is how we can essentially summarize what we've talked about with the different types of stars. Okay, so moving on to how we actually take measurements for stars and how we understand what they're made of. We do that by studying the radiation we get from them. So these are the different parts of the specification that you need to know and be able to do. So let's start taking a look. So to understand how all of this works, we first need to understand what the quantum model of the atom looks like. This is the atom diagram you often see, often called the planetary model of the atom. But to describe what it shows from a quantum perspective, we need to think a little bit differently. So in the quantum model, electrons behave like waves. So they don't occupy a single point in space, they occupy a region of space around a nucleus that we often call an electron cloud. However, there are some regions around a nucleus where there is a much higher probability of finding an electron, and that's what we describe as being an energy level, or in chemistry they'll tell you they're called a shell. So that's what we mean by the quantum model, essentially. So when we start thinking about electrons as a particle, what we start saying is we've collapsed the wave function. And what we find is when we collapse the wave function by interacting something with electrons, say a photon, for example, that means that the electrons are only allowed to occupy these energy levels. They cannot occupy a space in between them. And that becomes very important with all the observations from the quantum model. So what we're going to do is now start thinking about the electrons in terms of their energy. So electrons are going to have negative electric potential energy because the charge of the nucleus is positive, the charge of the electrons is negative. So when you multiply them together, you get a negative number. So they're always negative, and as you move to the energy levels closer to the nucleus, the electric potential energy gets more negative because you've decreased the distance from the center of charge. And that means to be able to move to those lower energy levels, they must have transferred energy to something else. And most of the time, that's going to be producing photons. So that's very much linking into the energy. So if you have some process that gives electrons more potential energy, so you might heat them, they might absorb photons, you might collide an electron into them, they move up to a higher energy level, and that's called excitation. And then to produce a photon, what they do is they de-excite, because being high in energy is unstable. Everything in the universe is trying to get to a lower energy level, and to conserve energy, it must emit energy in some form, and that is in terms of a photon. So in terms of calculating the energy the photon you produce, what you need to do is know the two energies that are energy states of the electron before it de-excited and when it's de-excited. And if you know the difference between those, you can calculate the photon energy produced. And this model of thinking about it explains to us why all of the atoms produce different wavelengths or different colors. So you should know, from those of you who've done chemistry and you've stuck stuff in a Bunsen flame, that they turn different temperatures when you burn them. So it's the same process here. So because every element has unique numbers of photons, every atom or element has its own unique energy levels. And therefore, the energy transitions, or energy gaps as they're sometimes called, are going to be different for every element. So then the photon energies, and therefore the wavelengths, will also be unique to every element. So we can make use of that in our study of the stars, because what we should get from a star is a continuous spectrum of light. Because they're incredibly hot, they emit light of all wavelengths. So if we measure the light from a star, we should see all wavelengths of the visible spectrum, and that's called a continuous spectrum. But what we can also get is, if we heat things to a lower temperature by sticking them in a Bunsen flame, for example, what we do is we give the electrons energy, and then they only produce certain wavelengths when the electrons de-excite again. And that's what we call an emission spectrum all of the wavelengths a certain element gives off. So we know which wavelengths correspond to which elements from producing these emission spectra. But what we get from stars are absorption spectra. So because the light from a star has passed through a gas as it's left the atmosphere of the star, we find some wavelengths are missing from the spectrum. So those look like black lines on the spectrum, and they tell us what a star is made of. Essentially, they tell us what's in the atmosphere around a star. So that's great. So we know that each element has its own unique wavelength, but how can we actually measure the wavelengths we are receiving on Earth? We need a device called a spectrometer, which is a fancy way of saying using a diffraction grating with some more pieces of kit. And we looked a little bit at this when we were looking at the waves part, but I'll just quickly describe the process. So we're going to use the diffraction grating equation. And what we're going to do is we are going to send our light wave through, and we don't know its wavelength, but we are going to choose a diffraction grating with a known slip separation, and we're going to measure the angle of diffraction to the first order, which makes n equals 1. So if we know d, we know sine theta, we can figure out the wavelength. That's the fundamentals of how it works. So if we think about the diffraction grating equation, we can think about how different things can affect the pattern that we get. So if we want to increase our angle of diffraction, that would be caused by a larger wavelength. So that's how we can compare several wavelengths. Longer wavelengths give us a larger angle of diffraction. But the other thing we can do is increase the slit separation. That would decrease the angle of the diffraction. So those are the factors we can use to affect the pattern, or we can just simply look at a higher order fringe. Again, that will give us bigger angles, which will make our measurements bigger, which would lower their percentage of uncertainty. So that would be a useful thing to do. Okay, so now we're going to start. Okay, so we've got a way of figuring out wavelengths that we're getting from stars, and those wavelengths can tell us the elements in a star. But we can also use them to get an estimate of the temperature of the star using Wien's displacement law. So it looks like this. So every star emits a certain wavelength with the highest intensity. It emits all the different wavelengths, but one of them in particular has the highest intensity. And what essentially Wien found is that wavelength is inversely proportional to the temperature. So if we know the temperature, we can get an idea of, if we know the wavelength with the highest intensity, we know what the temperature is, and we can do it using this equation here, and the constant is a fixed value that is given to you. So Stefan's law is a way of relating temperature to the luminosity of the star. So what Stefan's law says is the total radiated power in the form of emitting photons, essentially, it's directly proportional to the temperature to the power of 4. And we usually describe the radiated power as luminosity because most of the energy is in the form of light. So one of the things we can do is we can use these two laws. So Stefan's law is the one you can see there. The P, or the radiated power, is E, which stands for emissivity. And if we're dealing with a black body, which is what we assume stars are, that just has the value 1, so we can kind of forget about that. We have the Stefan's constant, which is shown by the lowercase sigma, the surface area, A, and the temperature to the power 4. So that's Stefan's equation, or the equation we use to model Stefan's law. So using Wien's law, what we can do is, if we know the maximum intensity wavelength, we can know what the temperature is. And we're going to put all of that to the power of 4, so we can substitute it in. So then we can put these two equations together. The surface area of a sphere is 4 pi r squared. So then we can rearrange it to get an expression for the size. So if we can measure the luminosity, we measure the wavelength, we can know also how big a star is. So we can see that by looking at the radiation, we know how big stars are, we know what temperature they are, we know how bright they are, and we know what they're made of. So we can learn a lot from their radiation. Okay, so finally, we're going to move on to look at some cosmology, so understanding the nature of our universe and how it behaves. So these are the things that you need to be able to do according to the specification. So there's quite a few in terms of cosmology. So let's start looking through those. So first of all, we've got a few different units of distance. So an astronomical unit, which is quite frequently used, is the distance between the centre of mass of the Earth and the Sun, and that has a fixed value. A light year, the distance travelled by light in a year in a vacuum, again has a fixed value. And a parsec, the biggest of the three, the distance of an object from the centre of the Earth with a parallax of 1 arcsecond, where 1 arcsecond is a degree divided by 3,600. So you can see that's the biggest unit of distance, and that's something we use quite a lot in cosmology to measure how far a star is away from us. Okay, so this is another piece of information we'd like, because we know how to measure a lot about stars, but we want to start thinking about how far away they are as well. So parallax essentially revolves around the fact that you need to see the position of something from two different positions. So we might go out one night on a nice clear night and locate a star that's of interest and measure its angle to the vertical. Then what we do is exactly 6 months later, we'd go out and measure its angle to the vertical again. And then what we do is we find the change in angle, divide it by 2, and then that will allow us to figure out what the parallax of a star is. And we're essentially doing it by comparing its position to something really far away. We consider it essentially stationary. So once we know the parallax in arcseconds, we can then calculate how far something away is in parsecs. So if theta is in arcseconds, d is in parsecs. So what we've got is a lot of stuff to make some calculations, but these are all based on this principle, the cosmological principle. So all our deductions about the universe are made based on this principle. So we assume that the universe is homogeneous, which means we assume the density is pretty much the same throughout. We assume it's isentropic, so we assume essentially its temperature on a large scale is universal throughout the universe, which is seems fair enough. And we assume that the laws of physics that we've developed here on Earth apply everywhere in the universe. So those are our assumptions when we're modelling. So we've figured out how to measure how far things are away from us. What we're next going to look at is how we can measure how fast things are travelling. And to do that, we use the Doppler effect. So generally speaking, what that means is objects that are moving away from a stationary observer will appear to be emitting longer wavelengths than they actually are. So the Doppler effect doesn't change what they're actually emitting, it just changes how they appear to the observer. And the reason this happens is that the time it takes the wave to reach us is increasing as the object moves away from us. That's the basic principle on which it works. So we can actually mathematically model that. So what we've discovered is if we can measure what we call the frequency shift or the wavelength shift, we can work out how fast that object is moving away from us, or the recession velocity, which is the symbol v. So now we've got ways of measuring distance and velocity. What Hubble did is he found there's a relationship between them. So what he found out is that the recession velocity of an object, due to the expansion of space, is directly proportional to the distance the object is away. So the further something is away, the faster it's moving away from us. And we use the Doppler effect, or these principles, to essentially explain how we know the universe is expanding. So we look at every star around our planet, and what we find is they are all redshifted, which means their wavelengths all appear to be longer than they actually are. And we know what they should be because they're all fusing hydrogen, right? So we know what wavelength they're actually giving out, and we know what wavelength they appear to be, so we can find the wavelength shift we call the redshift because they're getting longer. And what that means is that every object in the universe is moving away from us. And what that means is the universe must be expanding. And what Hubble's law tells us is that objects further away are moving away faster. And we notice that too, because we notice that their redshift is bigger, which means their recession velocity is larger. So it matches with Hubble's law. So Hubble's law has a constant that relates the velocity and the distance, and the constant is quoted in two different units very frequently, s to the -1, and it's also calculated in kilometers per second per megaparsec. So what we can look at now is how you convert between the two. So first of all, his constant in s to minus 1 is 2.2 times 10 to minus 18. And as we saw earlier, 1 parsec is 3.09 times 10 to the 16 meters. And so what we're going to do is figure out how many kilometers there are in 1 megaparsec. So we times by 10 to the 6 to turn it into megaparsecs, divide by 10 to the 3 to turn it into kilometers. So what I'm going to do is I'm going to rearrange that expression to just leave 1, because if we multiply any equation by 1, it doesn't fundamentally change the equation. So that's what I've done. I multiplied the 2.2 times 10 to minus 18 by 1, effectively, and you can see that when we lump all the units together, we get kilometers per second per megaparsec, and we get it as a value of 68, although the precise value of Hubble's constant has still not been identified. It still has quite large uncertainty, which is why our understanding of the universe is not as good as it could be. So the theory we use to explain all of this is called the Big Bang theory. So essentially, this theory states that what happened is at some point we call time equals 0, the universe was all concentrated into a single point of space. And then what happened is that after some event, the space and time started expanding. So space was not there before the Big Bang, but when the Big Bang occurred, whatever that was, suddenly space started expanding at a very fast rate. So this model was disputed for a very long period of time, so scientists had to collect evidence to support their hypothesis, and one of them is CMBR, or cosmic microwave background radiation. So this is radiation formed when the first hydrogen atoms were formed, essentially when the universe had cooled enough that the electrons and the protons were low enough energy to form an atom for the first time. So what happened is when the electron combined with the proton to form an atom, it lost electric potential energy and it therefore emitted photons. So there is evidence of this process occurring. And then due to the Doppler effect, these photons would appear much longer in wavelength than they actually are. And they would appear to be in the microwave part of the spectrum from our calculations. And that's exactly what we see now. So if the universe were static or not expanding, there would be no Doppler lengthening, so they would appear to be a much shorter wavelength than they would. But because they're microwaves, we know that means the universe is expanding because it must be for there to be a Doppler effect. So that's our first very major piece of evidence of the expanding universe. Okay, so for the next one, describing the impact of the Big Bang, I feel like I'm rehashing what I said earlier a little bit, but essentially it caused space to expand from a single point into the entire universe present today. And for one of the later specification points, I'll look at the stages that it goes through. So I'm going to go into this one in a bit more detail later on. But what we can do is we can use Hubble's constant as a way of working out how old the universe is, or getting an approximation for it. So Hubble's constant is equal to velocity divided by distance, which if you think about mechanics, velocity divided by distance should give you 1 over time. But that equation only applies if velocity is constant. So velocity is only equal to distance over time if velocity is constant. So assuming that the recession velocity has been constant, which it hasn't, which is why it's an approximation, if we do 1 over Hubble's constant, that tells us the universe is roughly 14 billion years. We've come up with better methods to estimate it since this one, but it gives you a nice ballpark figure and it's not too far from the real value we hold now. So, as I said, we're going to look at the stages of evolution of the universe in a little bit more detail. So, the first thing that happens, Big Bang causes space to expand, the start of the universe. So what happens very quickly is we get a period called inflation, and that causes the expansion to accelerate. Okay, so that's what happens next. So as the universe expands, it cools down. And the reason for that is everything's increasing its GPE, so it must be losing kinetic energy, so it must be cooling down. Because it's cooling down, the kinetic energy of the particles decreases, and they can start we start getting fundamental particles forming from pair production from the photons created at the start. So that's where our fundamental particles, our electrons, positrons, quarks, all of those kind of things form. So the universe continues to expand and continues to cool, and quarks start to combine to form nucleons like protons, neutrons, etc. That's what comes next. Following that, we start to get nuclei forming, so the protons and neutrons start to combine together to form nuclei, but we still have free electrons everywhere, so light still can't pass through space. And then what happens next is the first atoms of hydrogen form. So the first actual atoms form, and the radiation they produce is still around today, called CMBR. And the reason we can still see it now is because once the electrons are bound to a nucleus, light is now able to pass through space without being blocked by electrons, so which is why we can still see it. And then as we start to get atoms, gravity starts to pull them together into nebulae, and then we can start the process of forming stars, and we've essentially got to the age our universe is now in, the age of stars. Okay, so to finish off, looking at the constituents of our universe according to our current models of how physics works. So we currently reckon that about 5% of the universe is made of matter. That's our protons, neutrons, electrons, all of the things that we associate as the building blocks of everything. So we basically can't really see or measure 95% of our universe, which is really scary to a lot of people. The next component we've introduced that's about 20% of our universe is dark matter, and we need this to be able to explain how galaxies are able to form. Because without dark matter, the centripetal force in a galaxy would not be big enough, and so there shouldn't be any galaxies if there isn't any dark matter. And then dark energy, a whopping great 75% of our universe, is there to explain how the expansion of space is able to accelerate, because as you know, Newton's laws tell you that something cannot accelerate unless there's a force causing it to accelerate, and dark energy is there to provide that force to cause the expansion of the universe to accelerate, which our measurements tell us that it is. Okay, so that concludes this gravity and astrophysics part of module 5. I hope you found that useful to review your knowledge.